Okay, the next part here, we need to get into our three assumptions. We're going to have three assumptions for an independent measures analysis of variance. What's easy about this is they are the exact same three assumptions for the independent measures t-test. And as we already know, two of them are the same every single chapter. So one of our assumptions is for independent observations. Taking one measurement or set of measurements won't influence other measurements, right? Measuring one group won't influence the next group. Measuring one person won't influence the next person. Second one, normal distributions. We know our F distribution is not normal. We know it's positively skewed, but again, what we're really referring to here are the populations we're sampling. So if we've got a K of three treatment conditions, remember for independent measures, that means three different populations. Each of those populations needs to be roughly normally distributed. So that's been true for each chapter and remains true here. The bonus one that we had back in chapter 10, homogeneity of variance. It means the same thing it meant back in that lecture. It says that the variance values for each sample, in this example we've been doing all three samples, need to have equivalent variance values. They need to be close. Because again, we're combining these three different samples from three different populations all together into one study. So the example I think we used back in chapter 10 is if I took your height and your weight and averaged them together, what would it tell me? Nothing. They're such different sets of numbers that to combine them doesn't really tell us anything. So the same thing here. If I'm going to take the variance for each sample separately and put it all together to get a total variance to reanalyze, each of those sample variances need to be, again, equivalent, not exactly equal. And again, there's a formal way of doing it that we're not messing with, but our standard rule of thumb, if the variances are within 3 to 4 times of each other, all of them, then we're good to go. So nothing really new in the assumptions. The other thing I want to make sure to emphasize at this moment, before we go to the next example we're going to do, is don't forget to keep practicing your mantras. They're still going to be everywhere. They still apply in ANOVA. ANOVA is still a hypothesis test. So if sample sizes on the whole go up, error is going to go down, and if error goes down, your F statistic will go up and you're more likely to reject. If the variances, if the sample variances go up, then error goes up. And if error goes up, your F goes down, and if F goes down, you're less likely to reject. And the third mantra is still also true. Even though we talk about it as mean differences, that's not what we're calculating. The mantra remains the same. The further apart the means for the samples are, the larger F ratio we're going to get, the more likely we are to reject. So make sure you keep practicing, keep those mantras going in your brains, keep them fresh. So with that, we have covered all of the straight up lecture material except for one concept. And we're going to do one more example out of the book that will naturally bring that concept to bear for us. So I'll see you in just a minute for one more problem.